Hello everyone, here is the presentation video for my graduation thesis. My topic is better game playing agent with reinforcement learning. My project is based on AlphaGo Zero, a very famous Go player program developed by Google DeepMind team. In this video, I will explain in detail how AlphaGo Zero works and how I implement another game playing agent based on the idea of AlphaGo Zero. So hope you can enjoy this video. And now let's start. Here is the outline of my presentation video. Now I will start with the introduction part. Here is a short video from the lead researcher of Google DeepMind team on AlphaGo Zero.
AlphaGo Zero is the strongest Go program in the world. It outperformed all previous versions of AlphaGo. Specifically, it defeated the version of AlphaGo that won against the world champion Lee Sedol, and it beat that version of AlphaGo by 100 games to 0. So all previous versions of AlphaGo started by training from human data, and they were told, well, in this position, the human expert played this particular move, and in this other position, the human expert played here. AlphaGo Zero doesn't use any human data whatsoever. Instead, what it has to do is learn for itself, completely from self-play.
Now I will briefly introduce the game of Go and tic-tac-toe. So for both games, 2 players take turns to play, and the winning condition of the game of Go is to form larger territories. On contrary, the winning condition of tic-tac-toe is to occupy the whole horizontal or vertical or diagonal line. Here is the project objective and schedule. The objective of my project is to develop game-playing agents for a set of board games with the algorithms of AlphaGo Zero, and then propose a general framework for game-playing agent development of zero-sum game with perfect rules and information. Here is the schedule, and for the time being, I have finished all the work should be done in term 1. To better help with explanation, I will introduce some cartoon characters to represent the game-playing agent. So AlphaGo Fan, AlphaGo Li, and AlphaGo Zero. Go in Chinese is pronounced like Go, which means dog. That's why I introduced such a cartoon character. Then, description of the problem. So I've mentioned zero-sum game. A zero-sum game is a game where the sum of the gain or lose of utility of all participants equals 0. So if only 2 parties are involved, then the gain of the winner is paid exactly by the loss of the loser. So in some way, we can model both the game of Go and tic-tac-toe as zero-sum game. And this property makes both games suitable for machine learning. Also, the game of Go is a game with perfect information, which means in this game, players take turns to play and know all the previous events before they make any decision, including the initial states of the game. So for both the game of Go and tic-tac-toe, all the information is displayed on the board equally to both players. An example of a game without perfect information is a card game. So generally speaking, one player can't know exactly what cards the opponent holds, so he can't know the initial states of game, so this is not a game with perfect information. There are also some other important features that make the game of Go suitable for machine learning. So, well-defined rules. This means that the effect of any action can be known exactly, and the machine can judge the game result according to the rules itself without depending on human. Fully deterministic game. This means same sequence of action will always lead to the same result. Discrete game. So this allows some time for the machine to compute or simulate before a next move is taken. So in Google DeepMind's paper, they mentioned that the game is trained from scratch and without human knowledge. Actually, there is some human knowledge given to the machine, but it's very limited. So the rules of Go is given. A special scoring function to determine the winner is given. This is very special for the game of Go because in some games, at the end of the game, territories may not have been formed, so we need a special scoring function to determine the winner, and we do not need this for tic-tac-toe. The input features describing the board position are structured as an 19 by 19 image, and also the machine knows the rules of Go are invariant under rotation and reflection. The most important point is that no human manual on how to play Go is given to the machine. So similarly for our tic-tac-toe agent, we gave the rule of the game. The input feature describing the position are structured as an n by n image because we expand the board size of tic-tac-toe from 3 by 3 to n by n. And we also told the machine that the rules of tic-tac-toe are invariant under rotation and reflection. And similarly, no human manual on how to play tic-tac-toe is given. So there are actually many related works. The most important one is the Google DeepMind's paper on AlphaGo Zero. But we should notice that AlphaGo Zero actually uses a lot of computing resources, and it's far beyond what can be provided for my project. So I need to simplify the neural networks. And there are many other research on game playing agents for tic-tac-toe. There are many ways to implement an intelligent agent to play tic-tac-toe, and in my project, I mainly focus on how to implement the algorithm of AlphaGo Zero on a tic-tac-toe playing agent. So this way may not be the optimal, but I implement tic-tac-toe to help me get a deeper understanding of how AlphaGo Zero works. Then we'll go to the most important part, methodology. And in this part, I will explain in detail how AlphaGo Zero works. So for intuition, we may be curious about these 5 questions. Since no human manual is given to the machine, and no human history on how to play the game is given, so where does the training dataset come from? Actually, there are 3 phases of development. The first phase is to let 2 versions of the agent play against each other. This will be done for 25,000 games. So in this process, training dataset is created. So we know that Python is an object-oriented programming language. The best player at present can be viewed as a class. So we only need to create 2 objects of the class and let these 2 objects to play against each other. And at each move during the self-play, we will store the following 3 information. So what is the game state here? It's actually an image stack containing 17 layers. 8 layers are for the black side and 8 layers for the white side, and 1 extra layer is employed to indicate the player to play. So here is what a game state looks like. We have 8 layers for black, 8 layers for white, and an extra layer. For each layer is 19 by 19, and if there are stone on the position for the black, and on the first layer we will put an 1 there, if not we will put an 0, and we will do similar things to the white 8 layers. And for the last layer, if it is the black turn to play, we will put all 1 on this layer, and it's white, we will put all 0. So the other two information is the search probability and the winner. Search probability is a vector. So I will now explain how it comes from. So starting from a current state S, we have 3 paths, and during the simulations, we will choose the left path for 800 times, the middle for 200 times, and the right for 600 times. Then, in a very random mode, we will choose the lower node following the distribution of 0.5, 0.125, and 0.375. And for the winner V, it's a value. So if the player wins, we give +1. If the player loses, we give -1. And this value is only updated once one round of game is finished. So we will just like 2 versions of AlphaGo Zero to play to create training dataset for the next phase. So the second phase is the training the neural network. We will do optimization on the weights of the neural network and loop the process for 1000 times. And we have the third phase is to determine whether we should retain the newly trained agents or just retain the older one. So in this phase we have to set a threshold of winning rate. Please note that since AlphaGo Zero team have a lot of computing resources, these 3 phases are conducted in parallel and repeat again and again and again. So in phase 3, it's a very tricky method. In this way, we will ensure that a newly trained agent always competes with an agent with similar level of performance. This is very similar to how human learns to play the game of Go. When we are green-handed, we just play with someone who is not that good at the game and then learn from the experience. And later, when we become stronger, we also intend to find stronger opponents to keep us become better. So this is very similar. Now we have answered the first 2 questions. So phase 3 deals with how to improve the agent little by little. But we still have 3 questions to answer. To relax, so the basic illustration on the procedure of playing a board game is take a glance at the board and then decide where to place the chess piece. This is very natural for human beings. Actually, when we train the machine, we also follow the same process. So in the core of AlphaGo Zero, there is a neural network. And in AlphaGo Zero, different from AlphaGo, AlphaGo Zero only have 1 neural network, and it is responsible for both policy and value. So for a neural network, the first thing to clarify is the input and the output. For this neural network, it has 1 input and 2 outputs. The input is just the board state we have discussed before, and the output is a vector and a continuous value. So I will first talk about the input. Actually, the board is considered as a whole, and it is very similar to image processing problem. So we don't need to handcraft the features of a board. Instead, we just take maybe 17 pictures and make them as a image stack, and then give the stack to the machine. And the neural networks will give two output to each input, and that is to say each board state respectively. So traditionally, one neural network only have one output, but in the AlphaGo Zero neural network, it has two outputs. Here is what we have just discussed. So this is the neural network input. And for the output, recall that during self-play, for each move we store 3 information, and the game state is just the same as the neural network input, and the following 2 parameters actually corresponding to the 2 outputs of the neural network. And in this way we can calculate their difference, then define the loss function. So this is the second thing we have to clarify for a neural network. So in AlphaGo Zero, the loss function is defined as a formula, and it basically calculates the difference between what is the actual value and what is predicted by the neural network, and then take a summation. But there is a special term at last, so we call it L2 regularization. So L2 regularization aims at preventing overfitting or a too complex model. So here theta is a vector. If the model is too complex, then theta will have many components, and therefore the norm of the theta will become very large. And our goal is to try our best to reduce the loss function. So we will try a very large theta square from happening. So by minimizing the loss function, the neural network will actually finally learn what states will lead to win or losses, and give search probabilities similar to the actual search probability. The third thing to design is the network structure. So AlphaGo Zero follows the idea of deep residual network, or ResNet. This kind of neural network is proposed in 2015. It's a very new network. So what is a deep residual network? So it aims at tackling the problem of diminishing features and dropping accuracy when the network gets deeper. So for a traditional neural network, we only have one path going down. But for residual network, we have one path going down, we call it residual mapping, and another path just go directly to the output, we call it identity mapping. So if the neural network is fully trained and we add the new layer to it, then the data flow will just go through the identity mapping, but no data will go this way, all the data will go this way. So this helps reduce the diminishing feature problem. The identity mapping is also called shortcut connection. So now I will explain the details of the neural network in AlphaGo Zero. The most important part is the residual power, and residual tower contains residual block and other blocks, and I will now introduce the residual block. So it will go through this way, and I will explain later. Note that we also have a short path connection from the input directly to the escape connection. So here is a more illustrative image on the residue block. So we actually go through batch normalization and rectifier nonlinearity, and I will explain in detail here. So batch normalization aims at dealing with the problem that forward propagation is weakened in a multi-layer neural network. It tackles this problem by normalizing the data at each layer of the hidden layers. So rectifier nonlinearity refers to use nonlinear function as activation function in neural network. So if we only use linear function, then no matter how many layers we add, they are actually very simple. It's just some change in the linear coefficients. But if we introduce nonlinear functions, then we can enable the networks to handle intricate patterns. So here are some examples of the nonlinear function as activation function. After discussing the residue block, I will give a whole picture of how AlphaGo Zero design its neural network from the input to the two output. So the game state is given as the input, and then it goes a traditional convolutional block, and then goes to the residue blocks we just discussed, and then go in two ways. One way is goes through the policy head and then output the vector. The other way goes through the value head and output a value. So a convolutional block is defined in this way, value head in this way, and policy head in this way. Now we have tackled the first four questions, but we still have one more question to answer. So how does the agent choose its next move? This is implemented by Monte Carlo tree search, or MCTS. Actually, in both phase 1 and phase 3, MCTS is involved, but they are involved in different way. So it is MCTS that produces the search probabilities. So Monte Carlo tree search is, generally speaking, a decision-making method that combines the generality of random sampling with the precision of tree search. So a traditional MCTS contains these four phases. But in AlphaGo Zero, the simulation phase is replaced by the neural network. In this way, the neural network interacts with MCTS. So in each search process, the search is conducted to the end of the game, or it may quit earlier. And if it's conducted to the end of the game, the leaf node is input to the neural network for evaluation and get the two outputs, a vector p and a value v. For early quit, it is a system developed by Google DeepMind team to help save computational resources. So if I go through one way and I will probably lose, then below a resignation threshold, the machine will just stop at that node and quit the search process. So each node in the tree actually represents a possible transition from one ball state to another. Remember that a node represents a ball state, and actually an edge represents a transition. So an edge actually carries the following four parameters. So now I will go through how MCTS is conducted. So from the node S, we have to determine what is the next node. So we will choose the next node A that maximizes the formula, so it contains two parts. QSA is defined here, and USA is the upper confidence bound for trees, and USA is computed according to this formula, and CPUT is the constant. We can set its value. So our goal is to maximize the whole value. So USA is used to compensate for nodes that are rarely visited. So if NS is very small, then this value will be very large. And USA dominates at first, but as the search goes on, NSA will become bigger, and finally QSA will dominate. And for the backpropagation, each node on the path to the leaf node will get the following update. And for the leaf node, we will initialize its 4 parameters in this way. Remember that LA represents the edge from the node L to the next node A. Okay, then I will discuss in detail what is the difference between MCTS in phase 1 and MCTS in phase 3. So generally speaking, in phase 1 there is randomness, and in phase 3 there is no randomness. So we will repeat the search process, this process for 1600 times before we actually choose the next move on the board. So after running the simulation for 1600 times, the machine will choose the next move randomly for phase 1 or deterministically for phase 3. So if the machine is in phase 1, then it will choose the next move following this probability distribution, and if it's in phase 3, it will just choose the largest value. So we have know all the secrets about AlphaGo Zero, and after 40 days of training, AlphaGo Zero becomes the best Go player in the world. Then I will proceed to discuss how I implement the idea of AlphaGo Zero in my tic-tac-toe game playing agent. So as I mentioned before, due to the limit of time and computational resources, I have to simplify the neural network. I also have 3 phases of development, but I will play fewer games and loop the optimization for fewer loops. And I will set a different threshold. And these 3 phases are conducted in sequence but not in parallel. And since there may be many draw games in tic-tac-toe, the winning rate is defined by this formula, so in the denominator we exclude all the drawing games. In this way, we ensure that the agent we selected or retained will also always have no worse performance. And these 3 phases constitute one iteration. We actually conduct several iterations for the whole development. Similarly, for each move during the self-play, we state the 3 information. But since tic-tac-toe is much simpler, we only have 1 layer for the circle side and 1 layer for the cross side. For the game of Go, they have 8 layers for one side because the 7 layers below serves as the history indicator. It helps the machine to know which part of the board is actually being focused on. So It is very special for the game of Go, and we don't need this for tic-tac-toe. Similarly, we also have one extra layer to indicate the player to play. For the deep neural network, we also need to clarify three things: the input and the output, the loss function, and the network structure. So for the input and the output, I have discussed the input already, and actually similar to AlphaGo Zero, we also have one input and two output. For the loss function, we generally following the idea of AlphaGo Zero, but we delete the L2 regularization for reducing the difficulty of my implementation work. So for the network structure, I use traditional convolutional neural network instead of ResNet. So in this network, it contains fewer layers, just 4 CNNA layers plus 2 fully connected layers. But we do keep a policy head and a value head. So here is the overview of the network structure. So the game state S and the convolutional neural network layers and a policy head and a value head. So for the Monte Carlo tree search part, there are also some difference between the implementation in AlphaGo Zero and implementation in our tic-tac-toe agent. So basically we run fewer simulations before each move, and we don't have an early quit system. And for this constant, AlphaGo Zero set it to 1 in the first 30 simulations and then set it to infinite small, but we always set it to 1. So actually, since we extend the game of tic-tac-toe, we have to define the corresponding rules for the extended board. So for an n by n grid tic-tac-toe, a player will win when he occupies the whole vertical line, whole horizontal line, or the whole diagonal line. So based on our simplification, there are some benefits. So we reduce the consumption of computing power and also reduce the difficulty of implementation, but we have to pay some price. So first, the removal of L2 regularization in the loss function may cause overfitting, and the use of CNN instead of ResNet may lead to diminishing features when we implement the game on a large board. So the training environment is a shared GPU. It's very limited. So here is the testing part. So actually, I will first talk about what a perfect player for tic-tac-toe will look like. So for the traditional 3x3 tic-tac-toe, 2 perfect players will always end in draw. And actually for the 4x4 tic-tac-toe, 2 perfect players will also end in draw. So we gave a very simple proof here. So this is a strategy for the second player. In this way, the second player will always have a draw game. So by the symmetry of the board, the starting position actually have 3 different ways. And for the second player, he will just take these 3 actions. And for the next moves, when player 1 occupy A, then the second player just occupy another A, also B, another B. And in this way, the game will always end in draw. So this is the testing result for an agent for 4x4 grid tic-tac-toe. The effective training time is around 10 minutes. So actually, for one iteration containing 3 phases, the game is already being well trained. Also, I train an agent for a 6x6 grid tic-tac-toe, but the performance is not very good. So there is some problem here. Maybe the network structure is too simple, so some features is losing, or since I don't use the method exactly as it's used in the Google AlphaGo Zero paper, there may be explosion of the search tree. For AlphaGo Zero, after each iteration or each simulation, unused trees branch will be discussed, but I don't use this method. So maybe until this time, the Monte Carlo search tree is still not very well expanded. Actually, we know that a traditional tic-tac-toe is 3x3 grid. I start my first agent on my own computer, and then I build another version on GPU, and it takes less time, and also after one iteration the game is well trained. Here are two demo videos for the 4x4 grid tic-tac-toe I trained. In this video, machine takes the first, and actually I loses. So in this video I play with the agent I trained. The next video is I take the first turn, and I'm careful enough this time, and the game end up in draw. So I take the first turn and the machine takes the second turn. Okay, we have a draw game. So here are some conclusions and future work. So actually in this video I explain in detail how AlphaGo Zero works. And in this term I develop game playing agents for a set of tic-tac-toe games. And I modify the network structure of AlphaGo Zero to fit it into a simpler game with much less computing resource available. And for future work, I will continue to refine the structure of the neural network and try different parameter settings. And I will extend the 2D tic-tac-toe to 3D tic-tac-toe and develop related game playing agents. And finally, I will propose a general framework for game playing agent development of zero-sum board game with perfect rules and information. Here is my acknowledgement, and here are some references I refer to. Thanks for your time, and I hope you enjoy this video.